Welcome to Sheridan College's online video training for industrial electronic devices. After this presentation, you should be able to state Kirchoff's voltage law and explain how Kirchoff's law defines voltage in a closed loop. Kirchoff's voltage law states that the algebraic sum of all voltages around a closed loop electrical circuit equals zero. Or it can be plainly stated as the sum of the voltage rises equals the sum of the voltage drops. Kirchoff's law of voltages states that the algebraic sum of all the voltages in a closed loop will equal zero. What he's saying is that if you look at a closed loop circuit, which I have here, if you recognize this is Lab 2 series circuits, I actually have a battery which generates power, and I have resistors which consume power. The battery is actually a voltage rise, and each resistor exhibits a voltage drop. So what I'm going to do is do a measurement of all the voltages across the resistors. So look at R1, what I get is 0.93 volts. Write that down, 0.93 volts. Across R2, what I get is 1.31 volts. Across R3, 1.42 volts. Across R4, 2.32 volts. And across R5, 2.77 volts. Now what I'm going to do is measure the battery voltage. Whoa, my battery is getting real low. But it'll work just for this case, it's okay. But what I have is 8.71 volts. Let's look at the schematic and the voltages. R1 has 0.93 volts. R2 has 1.31 volts. R3 has 1.42 volts. R4 has 2.32 volts. And R5 has 2.77 volts. When we add these voltages all together, what we end up with is 8.75 volts. It's a little higher than the voltage we measured at the end, which was 8.71 volts, but that could have been because of the battery was draining as we were taking the measurements. The voltages were higher early in this experiment and dropped off very rapidly near the end. But we're only out by 4/100ths of a volt, which is actually very close. Now, if Kirchoff's correct, if I add all these voltages together, it should be very close to the 8.71 volts. So I will take 0.93 plus 1.31 plus 1.42 plus 2.32 plus, make that back, 2.77. What I have here is 8.75 volts. Probably this is a little higher because as I'm taking my measurement, the voltage across the battery is becoming lower, but 8.75 volts. As you can see, they are very close. Okay, I've changed the setup here a little bit. What I've got here is two D-sized batteries. They're actually connected in series, and when they're connected in series, the voltages are added. They're 1.5 volts each. So when you put them together like this, you should get something close to 3 volts. What I'm getting here is 2.99 volts, very close to 3. Now let's look at Kirchoff's law again. And we see that I'm going to take a resistance measurement. I only got 3 resistors here, and I've taken 2 resistors out of lab 2. So I put my voltmeter across here. I get 0.77 volts. I'm going to write that one down. There's my pen. 0.77 volts. Go across resistor 2. 0.84 volts, and across resistor 3 here, 1.37 volts. Let's look at the schematic again as it's changed. What we've done is taken and removed R1 and R5 from what we had originally. And now what we have, our R1 is the 47 ohm resistor, R2 is a 51 ohm resistor, and R3 is the 82 ohm resistor. So we have approximately 3 volts, 2.99 volts applied to it. With this, what we see is the voltage drop across the 47 ohm resistor is 0.77 volts. Across the 51 ohm resistor is 0.84 volts. And across the 82 ohm resistor, 1.37 volts. I'm going to add right now that you should notice that the higher resistance in a series circuit has a greater voltage drop. The higher the resistance in a series circuit, it has greater opposition, requires more electrical pressure to push the current through it. So if we total those up, it comes out to 2.98 volts, which is very close to the voltage applied. I think Mr. Kirchoff was correct. Now when I add these together, .77 plus 0.84 plus 1.37, what I get is 2.98 volts. When I measure my battery again here, 2.99. Addition here, 2.98 volts, and what I have is 2.99 volts on my battery. Again, we have just discovered that Mr. Kirchoff was right. Thank you for watching.